So we have this surface here, and there is actually friction. They tell us that there is a coefficient of static friction that is equal to 0.60. And we have a block on this surface that's connected by a spring to a train, little toy train engine of some kind. Oh, there we go, a little train. And we have a spring constant that is known. So we know the value for K here. K is 50 Newton meters, Newton per meter. And then we know that the toy train is moving forward at a speed of 5.0 centimeters per second. We know that the block is initially at rest because we're looking at when does the block start to slip. And we know that the block itself has a mass of 2.0 kilograms. So they're giving us a lot of information. They're defining t equals 0 to be the time when the train starts moving. We assume that the train instantly is moving at 5 centimeters per second at t equals 0. I'm going to use this in meters, so I'm going to make that 0.50 meters per second, just to keep in consistent units with everything else. So what I know is I know that there are going to be forces acting on this block. So as the train moves, that's going to apply a spring force as the spring gets stretched. So you're going to have a spring force there. And then you are also going to end up with an friction force that is acting backwards. It's going to be a static friction force. And so we have to remember a little bit about static friction, which is why I like having this unit here after we've done rotation and things. It's bringing us back towards linear motion. We'll also incorporate some rotation that could involve springs. But just refreshing our brain on some of these things we haven't done in a while. So if we have some sort of applied force, actually no, that's the friction force up. We're gonna have some friction force and we have some applied force. The idea is that if I apply no applied force, in this case the applied force is gonna be the spring force, then there's gonna be no friction force. And if I apply a little bit of force and it doesn't move, and a little bit of force doesn't move, a little bit of force doesn't move, a little force doesn't move, at some point in time it's gonna start to slip. And then that friction force is going to become constant. The slipping point right here occurs at Fs max. And remember, our Fk is usually less than that in this case. So we are looking for that slipping point. So the section which we're looking at, the friction force is going to be increasing linearly, and it's increasing linearly because the spring force is actually increasing linearly. So we're essentially looking for the instant where our spring force is at this maximum value and what our value for we would need. So this is actually an equilibrium position. So we have Fx, net force, is going to equal to our spring force minus the static friction force max, because we are at that slipping point. And what this allows us to do is it allows us to find basically the displacement. Is we could figure out how far has this spring been, well, I guess from its equilibrium position, so maybe it hasn't been stretched that much, but basically the train's been pulling it, so it has some sort of displacement from its equilibrium position. So my spring force would be K times delta X in magnitude. My Fs max is mu S times Fn, and that's going to equal 0. My normal force, I'm actually going to have a gravitational force here and a normal force up, but those are going to be equal and opposite. So since we don't have anything going at an angle, so that normal force is just going to equal mg. So solving for that displacement is going to be mu s mg over k. But I'm not looking for the displacement. I'm looking for time. Well, how do I get time? Well, in this case, the train is moving at a constant speed, which means the spring is being stretched and being displaced at that same constant speed. So because speed is constant, speed is displacement over time. Remember that if your velocity is not constant, if you're accelerating, this equation only gives you average velocity, but because in this case we're moving at a constant speed, then our average velocity is the same thing as our velocity. So if I wanted to find time, my time is going to be delta x over v. So what I can do is I can sub in for these values. So delta t is going to be mu s mg over k divided by v. Well, that's the same thing as mu s mg over k times v. So if you go through and sub in your numbers, so delta t is going to be mu s, which is 0.60, times your mass, which is 2.0 kilograms, times 9.8 meters per second squared, divided by your spring constant, which is 50 newtons per meter. Notice all of our units are in agreement, and we already did, oops, that's not supposed to be 0.50, that's supposed to be 0.050. So 0.050 meters per second. When you do that, you should get approximately 4.7 seconds. I realized that when I was looking at my answer key actually did calculate a displacement and then plug the displacement in over here. So there might be some rounding differences depending on what you did and the steps that you took. But that gives you an example here. So this is a dynamic situation because the train is actually moving, but because the block itself was in equilibrium, we didn't need to actually consider the acceleration itself of the block. There were no accelerations. Looking at this situation, we have a non-numeric problem where we have a block of mass m pressed up against an ideal spring that has a known constant k. The other end is attached to a wall. So if we take a picture here, this is a horizontal situation. Then we have a frictionless surface, so we don't need to worry about friction. And then it says we're basically going to compress it a distance of d. And then we want to find the maximum speed of the block after being released from rest. So we're going to compress the spring. If we think about what's going on here, we're going to release it from rest. So at this position over here, we have been displaced. We're like at x equals negative d if we wanted to assume that this was x equals 0 here. And then at x equals negative d, we're going to have a speed of 0, but we are going to have a spring force that is acting on that block, which means you are going to have an acceleration when you release it that is dependent on the spring force. So you're going to end up with the net force in the x direction at the instant of release is going to equal the spring force. There's no friction force. There is gravity, there is normal force, but there's no friction. So the only thing determining the horizontal motion is the spring force. So that spring force would equal mass times acceleration. Now the problem is that as it starts to move back towards the center, that the spring force is actually going to be decreasing. It is non-constant, which means our acceleration is going to decrease, which means our acceleration is not constant. So since I'm looking for a speed, I normally know that if I can find my acceleration, then I can use a kinematic equation to find speed. But the problem here is that the kinematic equations require the acceleration to be constant. So since our acceleration is not constant, that means we cannot do the kinematic equations. So how are we going to solve this? Well, if you can't do forces and kinematics, your other primary option is going to be energy. So if we look at this from an energy perspective, that the spring is going to have elastic potential energy over here at position 1. And we know that, well, our speed is going to be 0 over here, but we are going to have a displacement essentially of magnitude d. So our displacement is going to have a magnitude of d, so we're going to have potential energy. When we get back here to the center, our displacement is 0, So we're going to have no potential energy. So where did all of that potential energy go? Well, it went to our maximum speed. So when we look at this, there is not going to be any work done because if we assume that we are looking at the spring box system, that the spring force cannot do work. And generally that's what we assume, although you could assume instead that work is what is causing the potential energy. But if we look at the spring box system, then there's going to be no work done by the spring force. So we have K1 and U1, we have K2 and U2. So our K1 is initially 0. We're going to have some amount of elastic potential energy. But if we look over here, position 2, when we're at a displacement of 0, we're going to have no more potential energy. So that means that all of our kinetic energy had to have come from our potential energy. So K1 plus U1 plus work is equal to K2 plus U2. But work is 0, K1 is 0, and U2 is 0. So we get that U1 is equal to K2. So to arrive at this conclusion right here that U1 is equal to K2, you actually have to make a whole lot of assumptions, which is why you usually want to draw your diagram showing your assumptions or write an equation for work energy that outlines your assumptions. Now, once it reaches this point, because it's pressed up against and it's not attached, that means after it reaches the equilibrium position, the spring is going to be here at its equilibrium position, but the box is going to keep moving unattached to the spring. And because it's a frictionless system, the box is going to keep going. But sometimes you'll see when they work these problems is that there'll be no friction over here, but the box will reach an area of friction and then it'll slow down and come to a stop. So you can see this combined with say a problem with friction, where you use the spring to get it up to speed and then you use friction to slow it back down. Additionally, if the spring was actually physically attached, then the block would never be able to go too far. It would go back and forth, it would oscillate. And we'll talk about those oscillations in a little bit when we start talking about simple harmonic motion. But if it was attached, what would happen is it would get back out over here to a displacement of positive d. And when we're over here at positive d, we'll be back to a speed of 0. And because the spring force will now be in the opposite direction because the spring will have been stretched to that point, then it'll move back and it'll oscillate back and forth between negative d and positive d, with the x equals 0 being in the center. So just realize there's lots of different variations on this problem. But in this case, we're looking for Vmax. Vmax is going to occur over here at K2. U1 is going to be based on elastic potential energy, which is 1/2 K delta x squared, which is equal to K2, which is going to be 1/2 mv squared. So you can see that in this case, the mass of the block really does matter because mass doesn't cancel out from the spring constant over here. So mass is going to matter, the spring constant is going to matter. The 1/2s do cancel though, that's nice. And then if we assume that this is Vmax, then solving we get that Vmax is going to be K delta x squared over m square rooted. And that's the speed. If it had wanted the velocity, at that point the velocity would be in the positive direction, just in case it asked, because the square root means it could be positive or negative. So you're going to have this, if it was coming back towards the center, the velocity would be to the left, but it'd be the same magnitude as though it was coming off of a stretch or a compression.